Right, so this first question is about stearic acid, and it's asking about turning stearic acid from a liquid to a solid. And it's about a data logger and a thermometer. It says choose two advantages of using student A's apparatus. So why would a data logger be better than using a thermometer? Now you can clearly see the numbers on here only go in whole numbers or integers, whereas here we have them to decimal places. So because of that, it means there is a higher resolution. Now resolution is the scale of the instrument. So the resolution here is 0.1 and the resolution here is 1. Now that would be 0.1 degrees C and that would be 1 degree C. So this has clearly got a higher resolution, so we're going to tick that box. Another one is you are far more likely to misread the temperature if you read it yourself rather than a computer doing it, as this would link to human error. So I'm going to tick the second one as well. Student B removed the thermometer from the liquid each time he took a temperature reading. What type of error would this cause? Well, this could cause a random error, but I'm just going to go through what these mean. So a systematic error is caused by an instrument. So if the instrument is always wrong, then your experiment will always be wrong, and you would have to change the instrument. So this is caused by the instrument. So that is when the instrument you are using is always incorrect. A zero error is when it doesn't zero properly. So if you have a balance or a scale and you start it off at a non-zero value, then it will always be that extra amount. So if you start off by weighing something and before you put it on it's 0.1 grams and then you weigh it and it is 1 gram, then that's telling you that the 1 gram is incorrect because it's already started at 0.1 grams. So that would be a zero error when it doesn't start at the right value. Right, this is the kind of graph you will get for stearic acid. And the reason this happens is because the temperature will change and then at some point it's going to stay the same as it starts to change state. Okay, so this is called the latent heat. So the first question is asking us what was the decrease in temperature between 0 and 160 seconds. So between 0 and 160 seconds, that's 8.4 degrees C. So that's from this point here to this point here. It says use figure 2 to determine the time taken for the stearic acid to change from a liquid to a solid. So to change from a liquid to a solid, we're going to go from this point here through to this point here. So that is this range. So it's a liquid up until this point, and at this point here it's becoming a solid. So this range here is from 900, and we're going to subtract here, which is 160, and 160 subtracted from 900 gives you 740 seconds. So that's what the range is. On the next question, it says calculate the energy transferred to the surroundings as 0.4 kilograms of stearic acid changes from a liquid to a solid. So like I said, this was the latent heat of changing from a liquid here to a solid. So you've got this liquid phase right down to this point here, and then this is where it is a solid. Now, energy is equal to mass times latent heat. So our mass is 0.4 kilograms, and our latent heat, particularly this time of fusion. Now remember, fusion is when it turns from a liquid to a solid or a solid to a liquid, so that is the latent heat of fusion. So we're going to multiply that by 199,000, and that will give us 79,600. It says explain after 1200 seconds the temperature of stearic acid continued to decrease. Why is that? The reason for that is because stearic acid, which is a solid, has higher temperature than its surroundings, so it will continue to give out heat until it reaches the same temperature as the surroundings. So let's write that down. The stearic acid, the solid stearic acid, just going to put in brackets, the solid stearic acid, has a higher temperature than the surroundings. So it will continue to emit, which means to give out heat, until the temperature is the same as the surroundings. So is equal to the surroundings. You just imagine you had a box and this was 50 degrees C and it's in a room which is room temperature about 20 degrees C. This is going to give out heat until it becomes 20 degrees C. So remember, in terms of radiation, things always radiate from when they're hot to colder until they balance out, until they reach equilibrium. Right, the next question says, which one of the diagrams X, Y, or Z shows the arrangement of particles in a liquid? So that's this one, because we can clearly see they are randomly arranged but still close together. Now remember, when you're drawing a liquid, they have to be touching, but they have to be random. Solids are touching, but in a lattice formation, remember, and gases are far apart. So the answer there is Z. Which one of the following diagrams, X, Y, or Z, shows the arrangement of particles in a gas? Well, that is X. In a gas, the particles are they not moving? Well, that's incorrect. Vibrating in fixed positions? No, that could only be a solid, so therefore they must be moving randomly. In a solid, the forces between the particles are stronger than. That is why they only vibrate in their fixed positions, due to the fact that the forces are much stronger. Right, question 3 is about a kettle, and it says the energy transferred from the water in the kettle to the surroundings in 2 hours is 46,200 joules. So in this particular question, we're going to use the equation that energy is equal to the mass times by C, which is the specific heat capacity, times by theta, which is the temperature change. Now we're trying to calculate the temperature of the water in the kettle after 2 hours. So we need to rearrange this equation. So we're trying to find theta, so we need to remove m and c, so we're going to divide that on both sides by m and c, and that will cancel out. So our equation is theta is equal to energy divided by mass times the specific heat capacity. So what is our energy? Well, that's 46,000, so that's equal to 46,200, and we're going to divide that by the mass, which is 0.5, and then we're going to multiply that by 4,200, and that will give us 22 degrees C. Now, the initial temperature of the water is 100 degrees C, so that's when it's hot. Remember, we've just said that it's going to emit radiation, so it must get colder. So if it starts off at 100 degrees C, the temperature of the water in the kettle after 2 hours will be 22 degrees C less than 100, so 100 minus 22 gives us a temperature of 78 degrees C. So the temperature is 78 degrees C. Okay, calculate the average power output from the water in the kettle to the surroundings in 2 hours. So power is equal to energy divided by time. So therefore 46,200 from our previous page divided by the time taken. Now in 2 hours we've got 2 times 60, which gets us our minutes, and times 60 gets us our seconds. And that will give you 7,200. So if we divide those, we get 6.4 watts. Okay, I'm just going to bullet point this. Now remember, before you do any questions that have 4 or 6 marks, you need to think about what you're going to say before you start saying them. So let's just talk about all the key points and we can bullet point them. So for a solid, what are the most important points? The particles are in a fixed lattice pattern. They are close together. They have low kinetic energy. They vibrate. And they have strong intermolecular forces. And they're all the key points. So if you use these key points, you can pick the ones that are actually asked for in the question. In terms of So we're doing a solid and a gas. In terms of a gas, we can just look at the ones above and think, how is it in a gas? So particles are in a fixed lattice. Well, in a gas, the particles are randomly arranged. Are they close together? No, they're far apart. So we're looking at what we've written already and we're doing the opposite. They have high kinetic energy. Do they vibrate? No, because they're free to move, so free to move. And do they have strong forces? No, they have very weak / no intermolecular forces. Okay, what is meant by specific latent heat of vaporization? Now remember, vaporization is going from a liquid to a gas. So the word specific means 1 kilogram of. So we need to make sure we put that into our definition as it's for 2 marks. So it's the amount of energy required to change 1 kilogram of substance from a liquid, I'm just going to put L for liquid, to a gas. Okay, so the fact that we put 1 kilogram in there is going to get us an extra mark because the word specific is there. Right, the next question, we talked about this equation before. We know that E is equal to ml, and this is given to you in your equation list, and the mass is 0.018 kilograms, and we're going to multiply that by the latent heat of vaporization, which is 2.3 times 10 to the power of 6. If we do that, we get 414.00. So that's 41,400 joules. Right, so the next question is a really typical question that we need to know about, and that's about a graph. So we need to know what this is showing. So here we're having a state change. From A to B there is going to be a state change, and here we've got a temperature change. So remember, when we get this straight line here, we're going to have a state change. So we've got temperature increasing to -40, state change here, temperature increasing, and we need to know what's going on in terms of what the state change actually is. So from A to B, it's changing from a solid to a liquid. So this is the state change. So change of state from solid to liquid. Clearly, because it's at -40, there is no change in temperature, and that is really important. So when you're talking about latent heat and you're talking about a state change, there is going to be no change in temperature while all the internal energy of the particles starts to increase. So when all of them have got the internal energy to break their intermolecular bonds in a solid, they will then turn into a liquid. So whilst that's happening, the change in temperature doesn't happen. There is no increase in temperature because they are gaining their internal energy. Right, state change, sorry, for part B to C, this is not a state change, this is a temperature increase. So this is a temperature increase. And let's state what that is, from -40 through to 360 degrees C. Here there is no change in state up until point C. Now you can clearly see at point C, this is where it will start to change state. So at that point, we're going to have our boiling point. So this is where our liquid will turn into a solid. So temperature until 360 degrees, no change in state until liquid reaches 360 degrees C, and this is the boiling point. So when all the water is boiled, the temperature may increase. Right, the next question is about specific heat capacity. This is an apparatus you need to know for your exam. This is one of the assessed practicals that you need to be aware of. So you can clearly see there's a power supply with a thermometer and an electric heater, and this is for specific heat capacity. So before starting the experiment, the student drew graph A. Graph A shows how the student expected the temperature of the metal block to change after the heater was switched on. So the first thing is, what is happening in the graph? Well, clearly here we've got an increase in time, and here we've got an increase in temperature. But this relationship, if we start at 0 and it is a straight line, remember, is always directly proportional. So it is directly proportional as time increases. Now remember, we always talk about the x-axis first. So as we change the x-axis, what happens to the y-axis? Because the x-axis, remember, is the independent variable. So as we change the independent variable, what is happening to the dependent variable? So as time increases, the temperature increases. And this is happening at the same rate because it's directly proportional. Right, after 300 seconds, graph B shows the increase in temperature of the metal block is lower than the increase in temperature expected from graph A. Now, generally there's going to be a question related to specific heat capacity where you're expected to know that the energy is going to be transferred to the surroundings. So you might try and insulate this as best as possible, but there's going to be some heating of the air that surrounds it, so energy is transferred or dissipated to surroundings. Right, the power of the electric heater is 50 watts. Now we know that power is equal to energy divided by time, so we need to rearrange this for energy. So if we're dividing by time, we need to times by time, so that's the equation we're going to use. Our power is 50, so we need to multiply by the time, which is already in seconds, so we multiply that by 300, and that gives us 15,000 joules. Okay, so in the final question, the student uses the same heater to heat blocks of different metals each time the heater is switched on for 300 seconds. Which one of the metals will heat up the most? Well, clearly that's going to be the lead because it's got the lowest specific heat capacity, so it's going to be easier to raise its temperature by giving it a lower amount of energy. Now remember, the specific heat capacity is the energy required to lift 1 kilogram of material by 1 degree C. So you would need less energy to raise the temperature of lead by 1 degree C if you had 1 kilogram of that material. So in terms of the amount of energy needed to heat the metal block, a reason for your answer has to be in terms of that definition. So lead has the lowest specific heat capacity, so it will require less energy to raise the temperature by 1 degree C. So let's write that down. Lead has the lowest specific heat capacity, so it will require the lowest amount of energy to raise the temperature Now we don't know the mass, but we could say of 1 kg because it's specific by 1 degree C. Now these are all the mark schemes, so if you want to know the mark schemes, just keep playing the video.